Welcome to the session. This is chapter 2 itself, power semiconductor devices. Yes, the concept is thyristors concept that you concentrate on classroom workbook, that is based on topic that go through with the topic 3, that is classroom workbook. All of you take the workbook, that is classroom workbook. See the topic 3 in classroom workbook. This we are solving the questions based on topic 3, chapter 2. In thyristor concept, topic 3, third concept, third topic. Okay. That is mentioned in topic 3. Protection circuit, heating and cooling circuit of SCR. This is topic. Topic is given as protection circuit and heating and cooling circuit of SCR. Okay. Yes, concentrate. See the first problem. First question. Yes, ready? Topic 3, protection circuit, heating and cooling circuit of SCR. This classroom workbook. Yes. First question. Read once. Concentrate. For the circuit shown in figure, calculate maximum values of di by dt and dv by dt for the SCR. If R equal to 10 ohms and C equal to 0.15 microfarad. This is the given circuit. Okay. This is given circuit. In this circuit, for the thyristor, okay, across this, there is one snubber circuit, R and C combination. This is R, this is C, snubber circuit, and inductance is also given. This is how much? 15 microhenry. Load resistance is given as 2 ohms. Okay. The supply is root 2 into 230 sin 314t. This is a given set. R is given as 10 ohms. C is given as how much it is given? 0.15 microfarad. Then you calculate di by dt and dv by S. Concentrate. What is the solution for this problem, you tell me? To calculate di by dt, how to write the formula that I given in the design of snubber circuit parameters. Okay. Yeah. Then you can define voltage across the inductor. V equal to L into di by dt. Okay. Then how to write? How to calculate di by dt? Di by dt equal to V by L. But in the snubber circuit design that I given for assuming that DC supply. Even if AC supply is given, same formulas we are using. But if you take in the maximum value. Don't take RMS value. This is maximum di by dt, maximum dv by dt is designed based on maximum value of supply. Okay. Then what is supply? Root 2 into 230. The point to remember, if AC supply is given, in the calculation of di by dt and dv by dt, you take the maximum value, not the RMS value. That is root 2 into 230 by what the inductance is given? 15 microhenry. 15 into 10 to the power of minus 6. Then the value of di by dt, if you simplify this, do this, root 2 into 230 by 15, how much you can get? How much? To tell this answer? Okay, root 2 into 230 by 15. Yes, how much? Yes, that is how much? 21.685. This is di by dt na, that is amperes per microsecond. This is di by dt value. 21.685 amperes per microsecond. Clear? Then you want to calculate dV by dt also. Then to calculate dV by dt, how to write the formula? That no need to by heart. You write the formula of your own. Okay. Then you define the instantaneous voltage across the resistor. V equal to I into R. Okay. Then differentiate both sides. Then dV by dt equal to then di by dt into R. Okay. Now you are calculating dV by dt na. Then what is the dV by dt? dV by dt equal to what is di by dt? That is 21.685. 21.685 micro per microsecond into what is the resistance? 10. Then how much you get? 216.85 volts per microsecond. Okay. This is dV by dt. Clear? Like this we can calculate di by dt and dV by dt. Yes? No doubt. Yes? Concentrate. Question number 2. Read. All of you read one time. All of you read the question. Yes. A thyristor is placed between a constant DC voltage source of 240 volts and resist load R. The specified limits for di by dt and dV by dt for SCR is 60 amperes per microsecond and 300 volts per microsecond respectively. Determine the values of di by dt inductor and the snubber circuit parameters. Take damping ratio is 0.5. Yes. A thyristor is placed between a constant DC voltage source of 240 volts. What is the source voltage? Vs 240 volts. Okay. Now, what is the solution for this problem? Second one. Source voltage RV. V is how much? 240 volts. Okay. But load is R, but load value is not given. If it is not given, no need to take. Okay. Then di by dt is given. How much di by dt it is given? X. 60 amperes per microsecond. 60 amperes per microsecond. How much dV by dt is given? The value of dV by dt is 300 volts per microsecond. 300 volts per microsecond. The value of dV by dt is 300 volts per microsecond. Then take damping ratio is 0.5. Take damping ratio is 0.5. Zeta equal to 0.5. Then calculate di by dt inductor and snubber circuit parameters. Then you calculate first inductor. To calculate inductor, that means you calculate what is inductor and snubber circuit parameter, that is Rs and Cs. These values you want to calculate. Then to calculate inductor, you know first one, V equal to L into di by dt. Then what is L equal to? V by di by dt. Yes. What is V? It is given 240 volts. 240 by. What is di by dt is given 60 ampere per microsecond. 60 ampere per microsecond. 10 to the power of minus. Then value of inductance L equal to 4 microhenry. 4 microhenry. This is first one. What is the value of L we are calculated? L equal to 4 microhenry. Then we calculate RS. That I told how to write the formula. The instantaneous voltage across the resistor is defined as V equal to I into RS. Partial difference. This is the instantaneous value. This is the instantaneous value. That's why partial differentiate both sides. dV by dt equal to di by dt into RS. This relation you know. What is dV by dt is given 300 volts per microsecond. Okay. What is di by dt is given 300 volts per microsecond. What the di by dt is given? Yes, sir. 60 amperes per microsecond into RS. This micro cancel. Microseconds is cancelled. Then what is RS equal to? 300 by 60. It's okay. Then how much RS we can get? This is the snubber circuit resistance equal to 5 ohms. We get 5 ohms. This is the snubber circuit resistance. This is inductance and this is snubber circuit resistance. How much you can get? RS equal to 5 ohms. Then you are design inductance, you are design the resistance. Now you want to design the capacitance. I told that in the calculation of concept. In the concept I explained. If zeta is given, if zeta equal to damping ratio is given, then how to calculate snubber circuit capacitance? What is the formula for snubber circuit capacitance? The snubber circuit capacitance CS equal to 2 zeta by RS plus RL whole square into L. Okay. Then CS equal to 2 into 0.5 by RL is not given. What is RS? 5 whole square into L. L is how much we are calculated? 4 microhenry. 4 into 10 to the power of minus 6. Then how much CS we can get? 1 by 25 into 10, 4 into 10 to the power of minus 6. Okay. Then you simplify this. Then how much we can get? 0.16 microfarad. This is the calculation. RL is not given. If RL is not given, you take 0. Okay. 2 zeta. Zeta is given as 0.5. If it is not mentioned, how much damping ratio you take? Is 0.65. I told now. For optimum results, you take zeta equal to 0.65. If it is given, then according to that you can calculate. Therefore, then final result is, what is the value of filter inductor? Sorry, what is the value of di by dt inductor? 4 microhenry. What is the value of RS we are getting? 5 ohms. What is the snubber circuit capacitance we are getting? 0.16 microfarad. This is the final results. Concentrate. Note down. Read the question. All of you. Concentrate. Question number 3. Yes. A thyristor is rated. Sorry. A thyristor converter. This question number 3 na? Yes, concentrate. A thyristor converter of 415 volts 100 amperes is operating at rated load. Details of the thyristor used are as follows. On-state power loss 150 watts. The thermal resistances junction to casing 0.01 degree centigrade per watt. Casing to sink 0.08 degree centigrade per watt. Sink to atmosphere, that is ambient, is 0.09 degree centigrade per watt. Assume ambient temperature as 35 degree centigrade. The junction temperature for 100% load is dash. Okay. That is given as on-state power loss. what the average on state power loss? That is average power loss is given as 150 watts. Yes. The thermal resistances junction to casing theta JC, how much it is given? Theta JC is 0.01 degree centigrade per watt. What is theta CS? Casing to sink 0.08 degree centigrade per watt. Okay. Theta SA sink to ambient, how much it is given? 0.09 degree centigrade per watt. And ambient temperature is 35 degree centigrade. Ambient temperature TA equal to 35 degree centigrade. Then you calculate what the junction temperature. What the junction temperature. This is the question framed. Okay. Then what are the options it is given? Option A, it is given as 48.5 degree centigrade. Okay. Option B is given as 54.5 degree centigrade. 54.5 degree centigrade. Option C is given as 60 degree centigrade. Option D is given as 62 degree centigrade. Yes, concentrate. Tell me, what is the solution for this problem? Okay. Means you want to define from ambient junction. Means you want to define from junction to ambient. You want to define from junction to ambient. If you want to define from junction to ambient means, we know this. Average power loss equal to Tj minus Ta by theta Jc plus theta Cs plus theta Sa. This you know. Average power loss equal to, you are defining from junction to ambient na, Tj minus Ta by theta Jc plus theta Cs plus theta Sa. Then what is the average power loss it is given? 150 watts. Average power loss is 150 watts. What is the junction temperature that you want to calculate? What is the ambient temperature? 35 degrees centigrade. Ambient temperature is 35 degrees centigrade. What is the junction to casing thermal resistance? 0.01 degree centigrade per watt. Casing to sink 0.08 degree centigrade per watt. Sink to ambient 0.09 degree centigrade per watt. Okay, then you can define. You write this one. Tj minus 35 equal to 150 into, this is how much you get? 0.01, 0.08 point. This is 0.18. Okay. Then how much you get? Tj minus 35 equal to 150 into 0.18. This we can get 27 degrees centigrade. Na? Then from this, what the junction temperature? The junction temperature equal to 27 plus 35. Then how much you get? 62 degrees centigrade. Then which is the option? Option D is correct. Yes, all of you. A thyristor is rated to carry full load current with an allowable case temperature of 100 degrees centigrade for maximum allowable junction temperature of 125 degrees centigrade, and thermal resistance between case and ambient as 0.5 degrees centigrade per watt. Find the sink temperature for an ambient temperature of 40 degrees centigrade. Take thermal resistance between sink and ambient as 0.4 degrees centigrade per watt. Okay. Yes. The case temperature is given with an allowable case temperature of 100 degrees centigrade. This is given data. Tc equal to 100 degrees centigrade. Yes. For maximum allowable junction temperature is 125 degrees centigrade. 125 degrees centigrade. And thermal resistance between case and ambient. Thermal resistance between casing and ambient means casing and ambient. Casing to ambient means theta casing to sink and sink to ambient. This total is how much? It is given 0.5 degree centigrade per watt. 0.5 degree centigrade per watt. Okay. Then for ambient temperature of, how much it is given? 40 degree centigrade, and sink to ambient thermal resistance. Sink to ambient thermal resistance 0.4 degree centigrade per watt. Sink and ambient is 0.4 degree centigrade per watt. Then calculate sink temperature, heat sink temperature. This is the question is asked. Think how to solve this sink temperature. Then what is the solution for this problem? You want to calculate sink temperature. How to solve? Yes. Listen. Casing to sink and sink to ambient means first I want to define casing to ambient. Casing temperature you know, ambient temperature you know. You define casing to sink. Temperature you know, resistances you know, then first you calculate thermal power. If you want to calculate sink temperature means first you know the thermal power. Okay. To calculate thermal power, this data is given. I want to define casing to ambient. Define casing to ambient. Tc minus Ta by casing to ambient. Casing to ambient means casing to sink, sink to ambient. That means theta Cs plus theta Sa. Casing to sink and sink to ambient. Theta Cs plus theta Sa. It gives, this is average thermal power from casing to ambient. Now, what is the casing temperature? 100 degrees centigrade. What is the ambient temperature? 40 degrees centigrade. By what is theta Cs plus theta Sa? This is given 0.5 degrees centigrade per watt. Okay. This is how much average thermal power. This is how much you can get, you tell me. Then average thermal power equal to, this is 60 by 0.5. 60 by 0.5 means how much we can get? 120 watts. This is average thermal power. Now you want to calculate sink temperature. Sink to ambient it is given. Ambient temperature you know. You want to calculate sink temperature. Define sink to ambient. Define sink to ambient. Then average thermal power is remains constant because it is a series representation. The thermal power, the current is constant, just like thermal power is constant. Then average thermal power is same thermal power from sink to ambient by theta Sc, sink to ambient. Okay. Then what is the average thermal power? 120 watts. 120 equal to that you are getting. You want to calculate sink temperature, but ambient temperature you know. How much it is given? Ambient temperature 40 degrees centigrade by theta Sa it is given. How much theta Sa? 0.4 degrees centigrade per watt. 0.4. Then Ts minus 40 equal to 120 into 0.4. Then Ts minus 40 equal to 120 into 40. That 0.4, 48. Then Ts equal to then 88 degrees centigrade. This is the sink temperature. Okay. A sink temperature equal to 88 degrees centigrade. That you concentrate. Note down. Quick. Yes. Clear? See the next question. That is question number 5. 5 and 6 is totally theory questions. Question number 5. Concentrate, read the question. Snubber circuits are used to protect thyristor from which of the following? Snubber circuits are used to protect thyristor from which of the following? High dV by dt and low dV by dt, high dV by dt and low di by dt, low dV by dt and low di by dt, high dV by dt and high di by dt. Okay. Snubber circuits are used to protect thyristor from which of the following? It may be L snubber circuit or it may be RC snubber circuit. The point to remember, the solution, what is the answer for this one is? The answer for this one. Snubber circuit means L snubber and RC snubbers. It may be L snubber or it may be RC snubbers. Okay. L snubber is used to protect from, mainly snubber circuits are used to protect from high di by dt. High di by dt. RC snubbers are used to protect from dV by dt, but mainly it is a high dV by dt. To protect from high dV by dt. Yes, high dV by dt. Then which is the correct answer? It is used for high dV by dt and high di by dt. Generally, I told, generally snubber circuit means you take RC snubber circuit. But is the snubber circuits, it may be L snubber circuit or it may be RC snubber circuit. That's why, which is the correct answer? Option D is correct. You consider here L snubber circuit, but snubber circuit mainly used for high only, not for low value of change of currents. Clear? Okay, that for that answer D, that is option D is correct. Okay. In the same concept, topic 3, we go through with question number 6. Concentrate on, I'm reading the question. The thermal resistance between the body of a power semiconductor device and ambient is expressed as, that is, first one, voltage across the device divided by current through the device, average power dissipated in the device divided by square of the RMS current in the device. Option C, average power dissipated in the device divided by temperature difference from body to ambient, temperature difference from body to ambient divided by average power dissipated in the device. Which is the correct option? That you tell me. What it is given? Thermal resistance. How to define thermal resistance? You know this one. Thermal resistance is defined as thermal resistance theta equal to thermal resistance. Just like electrical resistance. How to define electrical resistance? Potential difference by current. Instead of potential difference, what you can write here? Temperature difference. Temperature difference. You can write temperature difference. Where you taken in the electrical, you taken current. Current is equivalent to thermal power. Thermal power. Okay. Therefore, the thermal resistance is defined as temperature difference divided by thermal power. Temperature difference from body to ambient divided by average power dissipated in the device. That's why, which is the correct option? Then option D is correct. For this, answer D is correct. Yes, clear? Okay, this about what exactly? Different models of questions asking based on snubber circuit and heating and cooling circuit of a thyristor. Okay, these problems you concentrate. Okay, this the classroom workbook. This is the models of questions is given. These are the answers you follow. Clear? Okay. Now, along with, for example, this is not given in classroom workbook. For example, in the same concept itself, If the question is framed like this, one example I am giving. This is not the question in classroom work. Generally I am giving. Example I am giving. Okay. If the question is framed like this, for example, okay. A thyristor, during operation of thyristor, if the question is framed like this, during operation of thyristor, during operation of thyristor, during operation of thyristor, okay. Junction temperature is 100 degrees centigrade, ambient temperature is 50 degrees centigrade, average thermal power is 50 watts. This is first case. Example I am giving. Okay. Junction temperature is 100 degrees centigrade. Ambient temperature is 50 degrees centigrade. In that case, average thermal power is 50 watts. Okay. If junction temperature is, is reduced to 70 degrees centigrade, at same thermal power, and ambient temperature, at same thermal power and ambient temperature, then percentage change in thermal resistance is dash. Percentage change in thermal resistance. If the question is framed like this, how to answer, you tell me? Percentage change in thermal resistance is dash. Okay. During operation of thyristor, junction temperature is 100 degrees centigrade. Ambient temperature is 50 degrees centigrade. In that case, average thermal power is 50 watts. If junction temperature is reduced to 70 degrees centigrade at same thermal power and ambient temperature, then percentage change in thermal resistance is dash. Can you answer this one? How to get answer this one? You tell me. In the first case, average thermal power equal to Tj minus Ta. Junction to ambient, you take total thermal resistance. Let assume that theta T1. In the first case, let the thermal resistance is theta T1. If the thermal resistance is theta T1, what is the average thermal power it is given? 50 watts. Okay. What is the junction temperature? 100 degrees centigrade. What is the ambient temperature? 50 degrees centigrade. Let this is theta T1. Okay. Then how to write theta T1 equal to, you tell me? Then 50 by 50. Then how much we can get? 1 degree centigrade per watt. The units of thermal resistance is degree centigrade per watt. Okay. In the second case, if the junction temperature is reduced to 70 degrees centigrade, then if Tj equal to 70 degrees centigrade, now you calculate thermal resistance. If Tj equal to 70 degrees centigrade means, then again same thermal power, that is PAV equal to Tj minus Ta by theta T2. In this case, let the thermal resistance is theta T2. Okay, thermal resistance is theta T2. Then what is theta T2 equal to, you tell me? This is 70 minus 50 by 50. Then how much theta T2 we can get? 0.4 degrees centigrade per watt. This is theta T2. Initial case, this is the thermal resistance, 1 degree centigrade per watt. If the junction temperature is changed to maintain same thermal power, then the thermal resistance will be changed. Then thermal resistance we are getting here is 0.4 degree centigrade per watt. 0.4 degree centigrade per watt. Now tell me, percentage change in thermal resistance equal to dash. Percentage change in thermal resistance. Percentage change in thermal resistance. How much? Percentage change in thermal resistance. How to calculate? This equal to theta T1 minus theta T2 by, that is theta T1 into 100. The percentage change in thermal resistance equal to theta T1 minus theta T2 by theta T1 into 100. What is theta T1? We are getting 1. 1 minus 0.4 by 1 into 100. How much percentage we can get? 60%. This is the percentage change in thermal resistance. This example I am not given in workbook. This additional example I am solving in the classroom itself. Okay, that you concentrate. Okay, how to solve the problem according to data. No doubt. Okay, this is about classroom workbook questions based on this chapter 2. The topic is, that is, snubber circuit and heating and cooling circuit of a thyristor. Based on heating and cooling circuit, that is snubber circuit, that you see the problem. Then go for, with respect to thyristor itself, the next concept I want to discuss, that is nothing but a series and a parallel connection of a thyristor. That is very important concept for any competitive point of view. In that series and parallel connection, first I will start with what is the necessity of series and parallel connection. Based on necessity, I will define two important factors. Then I will define in detail about what is the series connection, what is the problems in series connection, how to overcome those problems. Then what exactly parallel connection, what are the problems in parallel connection. Problems in the sense, during the parallel connection of thyristor or during the series connection of thyristors, there is some drawbacks or there is some problems or exist. Then to overcome those problems, what are the remedies we can take. All these concepts in detail I want to discuss. After discussing that concept, then we can solve some problems also based on the series and the parallel connection. That concept with respect to thyristor. If the thyristors are connected in series and parallel, that concept I want to discuss. Okay, clear? Okay. We will continue with the next session. That is the theory concept I want to start now. That will continue with the next session. The problems is completed based on this topic. In the next session, we will continue with the series and parallel connection of thyristors. Okay.